And then now that the recorder is started, I will get the screen share started. And we're in 4.3 still, but hopefully we'll finish that today. And let me move this taskbar out of the way because it blocks part of what I'm trying to read. I'm also going to scoot James over a little bit. He's a little in the way. Okay, got him. Okay. And let's see, what slide are we starting from today? Oh, wait, somebody else is trying to get in, but it's blocked the name, so I can't see. So let me see if I can find them down. Oh, here it is, Terrell. He's back. I already had marked him here, and he's back, so I'm glad Terrell is trying to get in again. Let me see if there's anyone else. Yep, he's the last one. Okay. I hate for people to be out there and I don't realize it, but I don't know if you can see this black box up at the top. Anytime someone tries to come in, it tries to block its name, so I can't see it. It's some stupid interaction between Zoom and PowerPoint or something that if something else pops up besides what I'm showing, it tries to block it and says, please move this window away from the shared application. Well, that's an important window. I can't move it in the beginning, but anyway, it's sort of crazy. Sometimes these technological features don't work that well together. Okay, so let's see where we are. That's what I was starting to do before. We're on example 7 on page 281. So let's see if we can find that. Yes.
Did you take roll already?
Yes, I got you when you were coming in. Yeah, I can see you in the waiting room, and I got you. So thanks for reminding me. I also saw you leaving the hospital, I think it was it?
No, I work in a physical therapy.
Oh, physical therapy place, okay. My wife was at a physical therapy place yesterday, okay. All right, so we're on example 7 on page 281. Let's see if I can work my way down to it. That's example 8. Okay. We're still under right triangles, no, the trig identities. So I'm a little too far along here. This, I think, is where we are. Yes. Okay. All right. Any other questions, issues, concerns before we get started today? Let's start from the current slide and we'll go from there. Now here's somebody else. Courtney is here. So here's Courtney. Let me get him in. Courtney is here. All right, pretty good attendance today. I can't tell if that's Courtney that's still being shadowed here or someone else is trying to come in. Ah, Damien's here. Let me get him here. See, they blocked my name so I can't see it. Damien is coming in. All right. That gets us up to 14, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Got it. The numbers are matching. That's good in a math class. Okay. All right. So I'll ask again, any questions, issues, concerns before we get started with where we left off before? We're in chapter 4, trigonometry, 4.3, right triangle trigonometry, and we're on page 281, bottom part of the page, example 7, using trigonometric identities. Okay, was that a question or just a big loud noise? Okay. All right, so example 7, I think I'll scroll through. Not going to let me scroll until I hit the screen again. This was example 5. We've already finished it. Long time passing. And just before we get to example 6. Okay. So let's go to, if there's no questions, we'll go to the whiteboard and pick up and go from there. Now, it's going to take me a little bit of time to maneuver things around here. There is a taskbar you probably can't see. I got to get out of the way so I have more room to write. And then I'm going to scoot this to the left as far as I can. And up as far as I can. So I have maximum whiteboard to write on. Okay. Then I'll get my ionizing pen and my Wacom board. And here's what we've got. If there are no questions, example 7. Let me pull my book over in my lap because it's hard to read from an angle. Use trigonometric identities to transform the left-hand side of the equation onto the right-hand side. And before we give anything else, they give us the domain we're working with. We're working from, looks like my color has changed. Let me change back to black. In some other class yesterday, I think I changed it and I never changed it back. So here we go, 0 is less than theta is less than pi halves. Where are we, Waldo? If our theta is between 0 and pi halves. What does that describe? First quadrant, between 0 and pi halves. Okay? And what we want to do is on these three expressions, here's the first one, that the sine of theta times the cosecant of theta is equal to 1. Now, we are trying to use our trig identities to transform the left-hand side of the equation into the right-hand side. Okay? In other words, we're trying to solve this for theta, is another way to say that. But one of the first things we do is use our trig identities. Which identity pops into your mind first? What would be the first thing you would suggest doing? Here's my little rule. Unless something else is pretty obvious, try to get everything in terms of sines and cosines. Okay. Now, what do I mean by obvious? If you have squares in there, the odds are you're going to be able to use a Pythagorean identity. So use that one. But if there's no squares and there's nothing else that says, oh, this is what you got to do, try to get everything in terms of sines and cosines. Well, this is already in terms of sines, so you're happy. So let's just write that down. Sine of theta. Now, what is cosecant of theta in terms of either sine or cosine? Anyone know? Get to know those identities. They're your friends. They're going to help you out of a lot of problems. What is cosecant identity? So, cosecant of theta. Anybody? If you got your books open, it's on the page right across from you. What is cosecant of theta? Okay, there we have hypotenuse over opposite. But in terms of your trig identities, you're absolutely right. Okay, let's do that. The cosecant of theta is hypotenuse over opposite. Now, among sines, cosine, and tangent, but especially sines and cosine, which one of those is related to hypotenuse and opposites? Sine or cosine? Either one of them? What other trig identity, either sine or cosine, uses the opposite side and the hypotenuse in its definition? Not the same definition, but in its definition. Remember some old hen? Sine of theta is equal to opposite over hypotenuse. So what would you say the relationship would be between sine and cosecant? Look across the page. What does it tell you? Cosecant is the reciprocal of sine. You flip them over. So this is 1 over sine theta. Okay? Now, you see that on the other page, page 280? The last of your, well, on your reciprocal identities, you have sine is 1 over cosecant, and right below that you have cosecant is 1 over sine. Well, look at what happens here. The sines divide out, and you're left with 1 is equal to 1. You've done it. That's all there was to it. The sines divide away, and you got left with 1 is equal to 1. You've made the left-hand side equal to the right-hand side. Okay? Let's do the second one. Maybe a little bit more involved here. Cosecant, so we've seen that one before, theta, plus cotangent theta times cosecant theta minus cotangent theta and supposedly this is equal to 1. Now we don't know if it is. I should have put a question mark here. That's what we're trying to show. Is it true? That's what an identity tells you, whether it's true or not. Is that equal to 1? Okay? Now, and by the way, the book did theirs the other way. They did sine as 1 over cosecant, and it still came out 1. Now, on this one, if you followed my first hint and changed everything to sines and cosines, that would work, but it would be a lot of work. This, you notice, algebraically, is multiplying this expression by its, and you remember this term, conjugate. The first term's the same, the second term's the same, the only difference is one's a plus and one's a minus. Those are conjugates of each other. And what happens when we multiply conjugates by one another? Anyone remember? If nothing else, you can FOIL it. First is cosecant squared theta. Cosecant times cosecant is cosecant squared. Then FOIL outer is cosecant by cotangent. So that's plus cosecant theta cotangent theta. Then the inner, FOIL, the inner would be plus cotangent. Oh, wait. This was a minus here, wasn't it? Yuck. Oh, there it goes. That's a minus there, because there's a minus with a cotangent. Okay. Sorry about that. That didn't get to draw. There we go. Okay, the innards is plus cotangent theta cosecant theta. I can't write. And then your last is minus cotangent squared theta. And the question is all that mess equal to 1? We don't know. But what we do know is cosecant cotangent minus cosecant cotangent as to plus cotangent cosecant, because multiplication is commutative, it doesn't matter which order, those add to 0. So you're left here with cosecant squared theta minus cotangent squared theta, because those middle two add to 0, and then it claims, but we haven't proven, that that's equal to 1. Now, remember the other thing I said when I said when all else fails, you can't think of anything else to do, get everything in terms of sines and cosines, okay? But one of the other things to watch for is anytime you have squares in there. When you have a square in there, think Pythagorean identity. Now, if you look across at the previous page, page 280, your three Pythagorean identities, though there's many others you could use, just rearrange these. That third one contains cosecant squareds and cotangent squareds. But it's not quite the same here. That says cosecant squared is, and let's write it in here if I can get my pen to cooperate. There it goes. Okay. Cosecant squared is 1 plus cotangent squared theta. That is what cosecant squared theta is. There's your Pythagorean identity. Then you have here a minus cotangent squared. And then the question, is that equal to 1? It sure is looking a lot more like it, because you could literally forget about the parentheses here because they're not really changing anything. Okay, so erase that and that. And when you do that, you'll notice I won't erase, I'll just draw. Plus cotangent squared minus cotangent squared is 0, and there you have 1 is equal to 1. Sure enough, that checks. You made the left-hand side look like the right-hand side. Now, if you look how they did it, I think they did it very, very similarly. They first multiplied the two together, and then they just wrote down the answer and said that's equal to 1. Okay. Yeah, if you can see that far ahead without plugging in the identity, yeah, you can do that. I think it was a little better to show all the steps. I don't know if I told you this before, but about a year and a half ago, I had just a grand old gentleman who was in my class. This was back when we were on campus. He took all three calculuses from me, and he griped about the calculus book. It was by the same author, but it's all the calculus books these days, by the way, and all the pre-calculus books the same way. They put all sorts of mess in there, but then they skip so many steps. Okay, and back when we both used the same book, he was about maybe close to a decade older than me, but I used the later edition. But we both used the book Calculus Text by Thomas, which was just a classic text. And he said Thomas always put every step in, showed you how to get every step. And he just griped like crazy that these new books don't do that. And he did have a point, but I always think of him when I see the book skipping steps. I thought, he wouldn't have liked that. Hold on just a second. I don't like to drink during or eat during class, but I've been going since 8:30 this morning. My throat's getting a little dry. Okay, so that was example 7. After every example, there is a checkpoint. Please try to do these checkpoints by sometime shortly after class is over. Okay, and those also, remember, if you don't want to turn in a problem, if you can't get a checkpoint to work, the answers are in the back of the book, and the checkpoints are at larsonprecalculus.com. That doesn't help you any. You can turn in that as well as a homework problem. Anything that's giving you difficulties, that's what I want to see. Okay. Any questions on example 7? All right. Let's go back to this PowerPoint 4.3. And we'll go back to current slide, and that was example 5, the end of 5. Let's move on to applications. This is on page 282, applications involving right triangles. Okay, now we've been doing our sort of the theory of it. Let's do some applications. Many applications of trigonometry involve a process called solving right triangles. Later, much later, we'll get to solving any triangle, but right now we're going to be solving right triangles. In this type of application, you're generally given one side of a right triangle and one of the acute angles. Okay? because you know one of the angles, if it's a right triangle, is going to be a 90-degree angle. So you're already given that one too, but you're only given, because everybody knows it's a right triangle, okay? But then you're given one acute angle on one side. You're asked to find one of the other sides. Or you're given two sides and are asked to find one of the acute angles. Something like that. In example 8, which is coming up, the angle you are to give is called the angle of elevation. The angle you're given. And it represents the angle from the horizon upward. That's the angle we're talking about, upward to an object. So here is example, well, no, not yet. In other applications coming up, you may be given the angle of depression. So maybe you're on top of a hill and looking down at something. That would be called an angle of depression. Now, usually we don't worry about clockwise, counterclockwise, and clockwise in that case. We just call them angle of elevation, angle of depression, okay? And just use them as acute angles, because we're going to assume the other side is perpendicular, and we're just going to use that. So don't sweat now that this might be a negative angle. Don't sweat it. Just call it whatever the measure is, okay? We'll be hitting that kind of stuff later. So angle of elevation is from the horizontal up, angle of depression is from the horizontal down, okay? And it could be going this way, angle of elevation this way, angle of depression that way. Hey, you don't have to say, oh, that's in third or fourth quadrant. No, don't worry about it. You're only dealing with the right triangle. It doesn't matter which direction it's going or anywhere else. Just dealing with the right triangle. So, here is example 8. A surveyor is standing 115 feet from the base of the Washington Monument. Now that looks like he's pretty close, but that's a pretty long distance, 115 feet. That would be about 35 yards or so, 33 yards. 35 yards, in fact, 35 yards, I believe, maybe further, from the base of the Washington Monument, as shown in the figure. The surveyor measures the angle of elevation from where he's standing to the top of the Washington Monument to be 78.3 degrees. Now here are your assumptions here. One assumption is you assume the Washington Monument stands straight up. And that's a pretty good assumption. In other words, it's perpendicular to the ground. Now if you've ever been in DC, you know most of the area where this is pretty flat, okay? Everything is pretty flat there, okay? I know it was a popular political slogan, sort of dumb, but still sort of popular, about draining the swamp. Well, I think that's how they built Washington, D.C. They filled in a swamp area, so everything is pretty flat, okay? So there's your assumption that the Washington Monument makes a right angle with the ground. There's your assumption. If this was the Leaning Tower of Pisa, you couldn't make that, but that's in Italy, okay? Don't worry about that. That's not what we're dealing with. We'll assume that is perpendicular, okay? So the question is, how tall is the Washington Monument? Now, I would have labeled this as probably H for height, or maybe T for tall, something else. They just called it Y. That's fine. You can call it anything you want to. That's what we're looking for. So you're given this measurement, the X value, you're looking for the Y value, and you're given the angle here. Now, my question is, what trigonometric function deals with this angle, this dimension, and that dimension? Which one of them? One of the trig functions deals with that. Which angle, the trig function of what angle deals with that? Now, let's just think for a moment. If this is your 90-degree angle here, which we're assuming it is, that would make this the hypotenuse for this angle here, 78.3 degrees. That would make your Y the opposite side. That would make the X the adjacent side. So what trig function of 78.3 degrees deals with the opposite and adjacent sides? Anybody? Please, somebody. How about taking oats away? Isn't the tangent of some angle theta equal to opposite over adjacent? Please say yes. Okay. This is back well before the trig identities. This was back at the bottom of page 277, the first page in this section. Tangent theta is opposite over adjacent. Okay? So we know this is tangent of 73.8 degrees. There's your theta in this problem. 73.8, 78.3. I said it right. I don't know what I'm saying. Okay, is equal to the opposite side. That's what we're looking for. The unknown here, y, over the adjacent side. We know that one. That's 115 feet. So you see, unit circle would be no good at all here because there isn't anything that's a unit. Right triangle trig, though, works perfectly. Well, if you're trying to find out what the height is, which is what your variable is standing for, how tall is it, that's your y, then multiply both sides of the equation by 115. So you get 115 feet, I'm going to keep the units for now, times the tangent of 78.3 degrees. That should equal y. Well, folks, pull out the handy dandy calculators. Okay? Hopefully you have one. Phones will work. That's what I'm using. Scientific calculator would probably be a little easier than a phone, but phones will work. Go to phone on the calculator mode. I need to do tangents, a trig function, so I'm going to have to turn the phone sideways to get to scientific mode and type in exactly what we got. Now, on my phone, I have to use sort of an awkward notation. For instance, that tangent of 78.3, I have to make sure I'm in degree mode, and on my phone, if I don't see anything up here, that means I'm in degree mode. Down here you see a radian. If you press that button, see, it goes to radian mode. If you press, now that's become a degree. If you press that, it becomes degree. Well, if you press it properly, the radian goes away, so that before you're in degrees. So I'm in degree mode. You have to make sure you're in the right mode. Scientific calculators are probably a little easier to handle than that, but that's how you do it on my phone. Okay? I have to enter the degrees first and then do the tangent. So I'm going to do, since I'm in degree mode, 78.3 and then press the tangent key. So there's a 78.3. The tangent key is sine, cosine, tangent, I think. It's hard for me to read backwards. And that gives me 4.8 blah, 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 irrational number. Multiply that by 115, 115, and you get another irrational number, but we'll round that one to about 555 feet. Okay? Now, the book probably does more than that, but that's what I get y to be. If I can get my pen to show up here, there it is. Y is approximately equal to 555 feet. Now, why did I just round to 3 digits? Well, they only gave us 3 digits here. They only gave us 3 digits there. I have no legal reason to think we can get more than 3 significant digits out of a problem. That's all you put in. The book, it does the same thing. It says about 555 feet. Any question on that? Was it obvious what we did and why? Or do you have any questions? Okay, let's see how the book did it. From the figure, you see that the tangent, and here they went to their definition, tangent of 78.3 degrees is, just like we said, opposite over adjacent. We knew that from several pages back. And we knew the opposite side was the y, which we were looking for. The adjacent side was the 115 feet, I think it was, that we knew. We already put in the angle we knew. We make sure we were in degree mode, and then we did the calculation. That's the same in this problem as your y over x, the way they drew it in the picture. See, they drew this as an x here. You didn't have to call it x. You could have called it a. I don't see why they called it x, but it's fine. Okay, y over x. And then where x is 115 feet, they left off the unit. Y is the height. That's what you're looking for. In feet. If the x is in feet, the y's got to be in feet. So that would be y is equal to x times the sine. What they did here, before they put the numbers in, they multiplied both sides of the equation by x. So they multiplied this side. If I can get my pen to show up somewhere here. Where is it? There it is. Okay. Multiply this side of the equation by x. Multiply this side of the equation by x. Here the x's go out because they're not zeros, obviously. And then you get y is equal to x times the sine of 78.3 degrees. Plug in the x, 115 times sine of that was 4.82 approximately. And that comes up right at close to 555 feet. Okay. Right after that example, guess what? There's a checkpoint. Please do the checkpoints as soon as you can outside of class. Okay. Here, let's see. Where are we now? Okay, they're skipping example 9. So let's go back one slide. And let's go to the whiteboard. And on the whiteboard, we will do example 9. All right, to erase this. All right, I hear no objection. So it erased. I didn't mean for it to, but it did. So here we have a picture. Guess I'll put this in my lap. It's heavy, but it's doable. Okay. I'm going to try to draw as close as I can to this picture in the book. I'm going to try to get it straight lines as much as possible, and I'll try to get it horizontal straight line as much as possible. This represents the beach road. Okay, I hope that's fairly close to horizontal. Not quite, but it's in the ballpark. Okay, we have a lighthouse down here. Okay, so I'm just going to go back to this one and draw my lighthouse in here. There's the light showing forth in the lighthouse. Okay, now this lighthouse is 200 yards from the bike path. That's not a road, it's a bike path. Okay, it's 200 yards from the bike path. So this is the bike path here. So let me get my, try to be a perpendicular line here, though I don't draw these well. So we'll try to get this to be, whoa, here's Jared coming in. Let me get Jared here. Hold on a moment. Hang on to that thought. There he is. Okay. Jared, you in yet? Okay. We're on we're on Chapter 4, Trigonometry, Section 4.3, Right Triangle Trigonometry, and we're on page 282, Example 9, the bottom half of the page. I was just trying to draw this representation of that problem, Example 9. Okay, and I'm trying to find my pen again. Ah, there it is. So here I'm going to try to get a perpendicular line This aggravates me, no end. Okay, perpendicular line from there to the lighthouse. Well, that may not be perpendicular, but it's fairly close. Oh, that's not far from vertical. And they tell us that is 200 yards from the bike path. That perpendicular distance there. Okay? And this is a lake up here, by the way. I didn't draw it in, but this, okay, this is the lake over here. Okay? Now, for some reason, the walkway to the lighthouse was drawn here. Now, let me again go back and get a straight line. This is how they put the path there, the sidewalk, okay, the walkway. Now what they tell us here is that that length is 400 yards. Okay, that's the walkway. Why didn't they not put it here? I don't know. That would have been a lot quicker. But no, they wanted you to get your exercise. Okay? What they're asking for is find the acute angle between the bike path and the walkway. Well, here's the bike path up here. Here's the walkway here. So this is the acute angle. Really cute, isn't it? Okay. Angle theta right there. That's what we're looking for. That's the unknown here. Okay. Now, again, we ask ourselves, which trig function relates this angle theta to this side and that side? What is this side called? Especially if this is indeed a right angle here, which I tried to draw it that way. This would make this 400 your what? Hypotenuse. And that would make the 200 your, no, that's opposite. The adjacent side would be this one. That's opposite the angle, okay, for this angle theta. So what trig function relates this angle to its opposite side and its hypotenuse? Please tell me you know that. Sine, exactly. Some old hen called another hen, blah, blah, blah. Okay, so sine of theta is opposite over a hypotenuse. Well, the opposite side was 200 yards. I'm going to keep the units there because a lot of times units are your friends. Over 400 yards. See, if one of these had been measured in feet or meters or something else, you'd say, hey, you can't do that until you get the same because the units need to cancel out, and they did. So that gives you the sine of theta is equal to that. Well, guess what? You could divide out 100 here, and then 2 will go into 4 twice, so that'd be 1 over 2, and you have that the sine of theta is equal to 1/2. Now, most of the time in real life, it's not going to be quite that nice for you. But this is one of our favorite angles that you know exactly what the sine is. And what angle would that be? Anyone? No. These are ones we've been talking about for a while. What angle theta gives you a sine of 1/2? You can either give it to me in degrees or in radians. I don't care much. I think the book gives it in degrees, but let's see. Yes, they do. Anyone know? Please say yes. That theta has to be either pi sixth or 30 degrees. Okay. Now my picture doesn't quite look like it. I didn't get that far enough out. But that's okay. And here's Sharika. Eureka, it's Sharika. Okay. Man, this is turning out to be a really good attendance day, I think. In my first class, I was only missing 2 students. In this class, I'm only missing, I think she's withdrawn. I'm only missing Jalen, I think. Wow, this is great, folks. Keep it up. I do believe Kelsey Hollis did withdraw from the class. I'm not sure, but I think I saw that. And then 2 others never showed, so I think they're out. So I believe we're only missing 1. That is great to see. Okay, any questions on that? Does everybody see how you get that? Now, this is jumping the gun a little bit, but I think I'll do it anyway. If you didn't remember your angle like that, and you had this statement here, sine of theta is equal to, I'm going to call it 0.5. That's another way you could write it. And you wanted to know what theta was. Well, just like addition undoes subtraction, subtraction undoes addition, multiplication undoes division, division undoes multiplication. A square root undoes a square undoes a square root. Well, those are inverse functions of each other. There is such a thing as an inverse sine function. So if you took the inverse sine, and we write it like this, of the sine of theta, you'd have to take the inverse sine here of 0.5. Take the inverse sine of both sides. This, the inverse sine undoes the sine, so you're left with the angle theta, and that's equal to inverse sine of 0.5. Well, here's how you do it on your handy dandy. I'm using my phone. If you got a scientific calculator, again, it'd probably be a little easier. Get to your science calculator mode, and you see right under the sine, cosine, and tangent, you have, oh, you don't, okay. Above that, over here, you have a second. You see second? If you press that key, I don't know if I got it, did I? Yes. And now what you have is inverse sine, inverse cosine, and inverse tangent. We want inverse sine, so with this on display here, remember I have to type the argument first, so 0.5, and then I'll press the inverse sine key, and that gives you, since I'm in degree mode, 30 degrees. So that's how you could get it on your calculator. Now we haven't gotten there yet, so that was premature, but I thought if you do run into a situation like that, you don't know the angles, make sure you're in the right mode, that better happen, and that you enter the thing. Now, of course, if you had been in radian mode, it's not going to give you pi sixth. It's going to give you what pi sixth is, which is 3.1415 blah 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 divided by 6, which is going to be a 0.5 something another, and you may not recognize that as pi 6, but that's what you get for not recognizing your angles. You should recognize those. Okay, so that was example 9. Now, any questions before we go back to the PowerPoint? Okay, let's go back to 4.3. We'll go back to current slide. Okay, we did Washington Monument. After this it says, by now you're able to recognize, weren't you, that sine of 30 degrees is the acute, that theta equal 30 degrees is the acute angle that satisfies that equation. You better get to know them. They've given them to you in 2 or 3 tables already. There's a reason for that. They want you to know those angles. 0, 30, 45, 60, and 90. Need to know those. All your trig functions of that one. Or in radian mode, that was 0, pi 6, pi fourths, pi thirds, and pi halves. Same deal. I was doing third quadrant, whatever. Okay, suppose that you were now in this case given an equation, sine of theta is equal to 0.6, and we're asked to find that acute angle theta. Okay, well, right now I've shown you how to do an inverse sine. They haven't done that in the book yet. So what we would have to know is sine of 30 was 1/2 or 0.5, and sine of 45 was 1 over root 2, which is 0.707 something another, but rounds of that. So you know it's something between 30 degrees and 45 degrees. Where in between there, we're not real sure, but you could have an estimate. If you did the inverse sine, you'd know exactly. Okay, so let's just see what it is. It seems like it's around 53 or so, but let's see what it is. Go back to that, turn it sideways. Oh, we're still in the second mode. So let's do 0.6 and take the inverse sine of that. And I get 36 almost 37 degrees. And that's between 30 and 45 degrees. Okay? So that was a pretty good estimation. Something between 30 and 45. 37 is almost splits the difference. Okay? But sine is not linear, so you can't depend on that. Well, I don't know why I put this back in my lap. I hope I won't need it again, but let's see. Let's move on. Oh, that was the last slide in the slide set. Not the last example, though. That's example 10 on page 283. So let's go back to our whiteboard. Okay, we're going to clear this out of the way. And we're going to solve a right triangle here. And here we want to find the length C and the height B of a skateboard ramp. So here's what they tell us. Okay, let me get my pen in straight line mode here. So I'm going to start the skateboard here. Well, I'm going to do the level ground here. I'm going to try to get it level and make that about 13 feet. Ooh, that's not very level, is it? Okay, and make that 13 feet. Okay, now we're going to take the vertex here and go up here. I'm just estimating that this is, if I can get my pen to show up, 18.4 degrees. Looks like mine might be a little too small. 18.4 degrees. Mine's not quite big enough. Okay, I also need a straight line here to go from here to there and try to make that a right triangle there. This drives me nuts. Okay, there we go. Now, we want to know how long that skateboard ramp is and what the B over here is, the elevation. We need to know two things here. Okay, now I don't think I need my book anymore. It's too heavy to hold in my lap. So let me get that back on the desk here. How would you proceed? And it really doesn't matter which one you do first. You decide what you want to go for first, B or C. Because you want to go for B. I like that too. And why? Why did you choose B? What trick? Okay.
It's not tangent.
Yes, it is. It's exactly tangent. Yeah, because tangent is opposite over adjacent. You know the angle. You know one side, you're looking for the other side is the opposite, so you hit it right on the nose. Tangent of 18.4 degrees is equal to opposite over adjacent. And to get what B is, that's what you chose to do first. B would be equal to 13 feet, multiplying both sides by 13, times the tangent of 18.4 degrees. Okay, pull out the handy dandy calculator again. It's already opened up. Get it here. You'll need to do it sideways here to get it in scientific mode. And again, with this calculator on my phone, I have to do the 18.4 degrees first. So I'm in degree mode. Make sure you check that first. 18.4 degrees. Take the tangent of that. Oops, I'm in the second mode. So I need to go back to tangent. I was in inverse tangent. I need to go to that. 18.4, take the tangent of that, and then multiply that by 13. And that gave me B to be approximately, I'll call it 4.32 feet. Now the reason I set it that way, this is only two significant digits here, so I should call that 4.3. But they gave you 3 digits here, so I'm going to give you 3 digits here too. You really don't. It should be the other. Okay? Now, that gave you B. How do you get C? And again, you ask yourself, what trig function relates this angle, that side, and this side of the right triangle? Assuming that is a right triangle. What is this side called? The side opposite the right angle. That is your strange Greek word. It's not another taking, it's not oats or away, it's your hypotenuse. So what trig function relates this angle, the adjacent side, and the hypotenuse? Please say you know. Caught another hen. Whoops. Cosine theta is equal to caught another hen. Okay? So there we have it, that the cosine of 18.4 degrees is equal to the adjacents on the top. This is your adjacent side to that angle, and that would be 13 feet over C, the hypotenuse. Now, this is going to take a little more work because you need to get what you're looking for up top. So let's multiply both sides of the equation by C. So this will be C times cosine of 18.4. I want to get C by itself. By the way, the C's here go out. And so I'm going to divide both sides here by cosine of 18.4 degrees. Okay. Now, on my calculator, that really gets a little awkward. But I think I can still do it. I'm going to try it anyway. Okay? So I'm going to clear what I've got on the screen now. Okay. So I'm going to do 13 divided by, I have to enter my argument first. I'm still in degree mode, so that's okay. 18.4 cosine, and then press equal. And what do you get? At least in my calculator, I get C is equal to, I'll write it here, approximately equal to 13.7 feet. Okay, and that kind of makes sense, doesn't it? This is a very, very, very short side here, and so these two are close to the same length. Always the hypotenuse is longer. 13.7 gives it to you. Now some of you could be saying, wait a minute, you didn't need to do that, did you? If you know two sides of a right triangle, you know the third side as well. You could have done a squared plus b squared is equal to c squared. Now the reason I didn't do that is this was a calculated value, right? I can't get my pen to show up. Where is it? There it is. This is a calculated value. I'd rather use the two values that were given because that's the greatest precision there. So by using those, I use the cosine. And I get 13.7 feet. Let's see what the book got. They got 4.3. Look at that. They did it better than I did. I thought for sure they were going to give too many digits. They only gave 4.3 feet, which is actually what you should do. And the C was 13.7 feet. That's actually more digits than you needed, but to call it 14 is a little bit of a stretch, but that would have been okay too. So yep, both of those is what they got. Any questions on that? Okay. Now, there is a checkpoint following every exercise. Please do the checkpoints, every example, I'm sorry. Following every example, please do the checkpoint as soon as you can outside of class. Okay? Now, that checkpoint, okay, I don't know what the beam was about. Let's just make sure nobody else is trying to get in. Okay, I don't see anybody else. If y'all sense anybody else trying to get in, please let me know. Okay. There is a little summary at the bottom of the page which goes over some of the key definitions and concepts. But then on page 284, 4.3 exercises, the first 4 exercises are vocabulary. Now, the first one is match each trigonometric function with its right angle definition. Okay? Now, I don't know which way you want to do. If any of you have your books, would you rather I give you the trig function and you tell me the definition in terms of the names of the side like we were doing, opposite, adjacent, and hypotenuse, or if I give you the name of the ratio, you tell me the definition, you tell me which function. Which way you want me to do? Call out the function, you give me the definition, or me call out the definition, you give me the function. Name it and claim it, folks. Is anyone still there? Okay, you want me to give the definition. Okay, the first definition is hypotenuse over adjacent. What is that? Which trig function? Hypotenuse over adjacent. That's secant, perfect. What is adjacent over opposite? Perfect. What is hypotenuse over opposite? Hypotenuse over opposite. Help me somebody. Cosecant, excellent. What is adjacent over hypotenuse? Cosine. What's opposite over hypotenuse? And what is opposite over adjacent? Tangent, yes, y'all know them. Okay, number 2. Relative, this is fill in the blank. Relative to the acute angle theta, okay, The three sides of a right triangle are the blank side, the blank side, and the blank. Okay, we just named all three of those before. What are they? Opposite side, adjacent side, and the hypotenuse. Perfect. Number 3. Cofunctions of blank angles are equal. Cofunctions of blank angles are equal. My goodness, your hair looks nice today. Or that's a pretty dress or shirt. Complementary angles, you got it. Cofunctions of complementary angles are equal. Number 4. An angle of blank represents the angle from the horizontal upward to an object, whereas an angle of blank represents the angle from horizontal downward to an object. What's that first blank? Elevation. The second one? Okay, take some Prozac. No, I'm just kidding. Okay. All right, never mind. All right. Then homework exercises here would be, do any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. Do either 11 or 13. They're both at Calc Chat. Yes. This is page 284, starting at 284. It's going to go into 285, into 286, into 287. So 4 pages worth here. I'm starting in 284 here. So any of the odds 5 to 9, all 3 of those are at Calc Chat. 5's at Calc View. 11 or 13 are both at Calc Chat. 15 through 21 are all at Calc Chat. 23 through 27 are all at Calc Chat, with 27 at Calc View. 29 through 35 are all at Calc Chat. 37 through 41 are all at Calc Chat, with 39 at Calc View. 43 through 51 are all at Calc Chat. 47's at Calc View. 53 through 57 are all at Calc Chat. 59 and 61 are both at Calc Chat. And then you have a bunch of applied problems like we were just doing at the end. Any of the odds 63 through 73. They're all at Calc Chat. Then 75 through 79 are true-false. They should all be at Calc Chat. And then you can think about doing 81 or 83. Either one of those or neither. It doesn't matter. But they should both be at Calc Chat. And those wind up on 287. Any questions on 4.3? Okay, we're ready now to start 4.4. So unless there's any question, let's go to the new slide here, and we'll go to 4.4. Now, let's go from current slide. Okay, we're still in Chapter 4, Trigonometry. 4.4 is dealing with trigonometric functions of any angle. Now, if you recall, 4.3 was doing right triangle trig, and in right triangle trig, your two angles that are not the right angles are both acute angles. Okay, so now we're going to move to trigonometric functions of any angle, not just acute angles, nice acute angles, but any angle. Negative angles, obtuse angles, any angle. Okay, we did this on the unit circle. We're now going to do it with right triangle trig too, so to speak. Now, let me say this. After we finish 4.4, that's time for test 1. Okay, so I'm guessing this will be probably, I'll have the test ready for you on Thursday. Whether we finish 4.4 or not, I'll go on and give it to you on Thursday, probably after class. And if we didn't quite finish 4.4, don't worry about the problems that we didn't cover, but it'll give you plenty of time to work on the other. It's a pretty long test, so I'm wanting to give you as much time as possible to work on it. Technically, it's supposed to be a week. I'll give you as long as you need, as long as you get it into me before I give you the next test, which will be at the end of 4.8. So There is a deadline, but anything in between. Try to get it to me as soon as you can rather than later. So let's move on to 4.4, trigonometric functions of any angle. Here are your objectives. We evaluate the trigonometric functions of any angle. That's what we said we're going to do. In doing that, we're going to find what they call reference angles. Okay? Nice things to get to know. And we'll evaluate trig functions of real numbers, which is what we've always been doing. These are real numbers. These angles are real numbers. Usually when they say that, they mean in terms of radians, but any real number. Okay. So introduction here is first, have you seen these before? Okay. The definition of trig functions were restricted to acute angles. In this section, the definitions are extended to cover any angle. When theta is an acute angle, the definitions here coincide with those in the previous section. However, when you get to obtuse angles, we weren't talking about those before, but guess what? The values are still true. Okay? Now, rather than calling them opposite, adjacent, and hypotenuse, which you still can do, they're now going to call them x for the adjacent, y for the opposite, and r for the hypotenuse. Okay? Now, here's the drawing while this is fading out. Let me show you. Here's an obtuse angle greater than 90 degrees. Here's the horizontal side. Here's the vertical side. Here's the point that we're interested in. Okay? In this point, the x happens to be negative. The y, though, still is positive. The r, by the way, is always, always, always positive. Because what is y? The principal square root of x squared plus y squared. Now this may remind you of the unit circle. In the unit circle, r was always 1. Okay? Now r is any length based on what the x's and y's were. Okay? So this is the time that please don't confuse what we're doing here with the unit circle. That required r always to be 1. Then you figured out what x and y were. Now you're given x and y, and you calculate what r is. So given this, again, remember I said the y was the opposite side, the x was the adjacent side. Okay? Because this is your angle theta. Now later we'll talk about it. Its reference angle is from here. The opposite side of that is your y. The adjacent side is the x. So just keep that in mind. Y is always opposite. X is always adjacent. R is always your hypotenuse. So here you have same thing. Sine of y, opposite over hypotenuse, y over r. Cosine of theta, adjacent over hypotenuse, which is x over r. Tangent is opposite over adjacent, y over x. Now, well, we'll get to that later. Remember here, now up here, r can never equal 0, ever. Because if you're in any point other than the origin, your x or your y or both are going to be numbers not 0. And once you do a number not 0, square it, it becomes a positive number not 0. Add that to another number not 0 squared, you get another positive number. Add those two together, you get a positive number. The square root of that positive number, principal square root, is positive. Never 0, always positive. Okay? However, x could be 0. That's why you don't worry. R can't be 0. It's got to be positive. X could be 0, so you have to exclude that. Your cotangent, of course, is adjacent over opposite, which is x over y, and here the y can't be 0. Secant is the reciprocal of cosine, which is r over x, but here again x can't be 0, so therefore tangents and secants are related to each other insofar as x can't be 0. But if you think about your Pythagorean identities, it's tangent squared plus 1 is equal to secant squared. They always are related. Cosecant is again the reciprocal of sine, so that's r over y. Now y can't be 0, and that's where the cotangent and cosecant have in common. Their y's can't be 0, but that's why in the Pythagorean theorem, 1 plus cotangent squared is cosecant squared. Okay. Any questions on that? Same table you've had before, they just changed the letters around. Okay. Any questions? Let's see, was that somebody coming in? I don't think so, but let me see. No. Okay. How are we doing on time? Oh man, we only got 2 minutes, don't we? See what we can get done in 2 minutes. Because that r is the square root of x squared plus y squared, unless you're at the origin where x and y are both 0, then r would be 0, but of course you don't have an angle then. Okay, you're not anywhere off, in any of the quadrant. So that won't be the case. R is always positive. It cannot be 0, always positive. It follows that the sine and cosine functions define all real numbers. No limits there, because they're always, the sine is y over r, the cosine is x over r. Never is your denominator 0. So they're defined for all real numbers. However, when theta is equal to 0, the tangent and the secant of theta are undefined. So theta is not defined when is x 0. That would be anytime you're on the y-axis. So at pi halves, and at 3 halves pi, or at negative pi halves, anything on the y-axis, not tangent and secant, not defined. Okay, so the tangent of 90 degrees, undefined. Similarly, when y is equal to 0, that's on the x-axis. So at this end or that end, either end of that, not the cotangent and cosecant are not defined at 0 or pi or any multiple of pi. So tangent and secant are not defined at your half pi's. Tangent and cosecant are not defined at your whole pi's. Okay. Do we have time? Nope, we just run out. So we'll be starting next time with example 1. So I'm beginning to guess here that maybe we won't finish 4.4 next time. We might. This is sort of not a super long section, but there's a lot of material in here. So homework exercises, we didn't do any examples here, so the homework exercises will just be from 4.3. So any of those will work. Any questions? I'm sick and tired of sharing, so I'm going to stop sharing here.
Was this lecture recorded?
Yes, it is. You can't see it over here, but it is the hour and 12 minutes and 50 seconds. So yeah, most of it was. Only when I was calling roll at the beginning did I not record. So yeah, I'm going to turn it off though. I'll try to remember to do that. Good question. I'm glad you brought it up. Anyone else? Any other questions, issues, concerns? Okay, for those who did come in late, depending on how far we get in 4.4 next time, it's sort of a long section, lot there. If we get far enough, I'll go on and give you your first test next Thursday, understanding you may not be able to do everything in it because we may not have covered everything, but at least it gives you the weekend to get started on it, because it is a pretty long test. And then we'll probably finish 4.4 on Tuesday, and at that point, that's when the clock starts for you to turn the test in. But you can take as long as you need to, as long as you get it into me before I give out the next test, which will be at the end of 4.8. All right, any questions, issues, concerns? All right, then I'm going to end the meeting for all. I already had a few people leaving already, so we'll see you on Thursday. Good attendance today, folks. Take care. Bye-bye.